Hello and welcome to video 2. In this video we'll be looking at powers, surds and standard form. So first we start with powers. If we have a number, say 2, and we want to apply a power of 3 to it, that is the same as writing 2 times 2 times 2. Again, this is assumed key stage 3 knowledge. If we have 5 to the power of 5, that's 5 times 5 times 5 times 5 times 5. Essentially, this bottom number, the base, is the number that we're multiplying, and the power, or the index, is how many times we're multiplying that number by itself. You need to know the powers of 2, 3, 4 and 5, so 2, 3, 4 and 5. Anything to the power of 0 is 1, and the powers of 2, 3, 4 and 5, well, we can do those. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 16, 32, 64, 128, 256, 512, 1024, and you can see that we are simply just doubling every time. And then we have 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27, 3 to the 4 is 81, 3 to the 5 is 243, 3 to the 6 is going to be 3 to the 2 times 3 to the 2 times 3 to the 2, so 81 times 9. 81 times 9 is 729. And you can see that goes on. 4 to the 1 is 4. And we have 16, 64, 256. And you can continue that too. And for 5, we have 5 to the 1, 5 to the 2, 5 to the 3, and 5 to the 4. We can also apply roots to the results. So if we had 3 squared equals 9, well, we know that's 9. If someone asked us x squared equals 9, what is x? Well, we can do the root of 9. The root of 9, there is essentially a 2 here, but when it is a 2, we don't tend to write it. You can just write the root of 9. The root of 9 is either 3 or, and this is an important or, minus 3, because minus 3 times minus 3 gives 9. Now, generally speaking, if we can apply the root using any power, so any index. So if we have x to the 4 equals 81 and we want to find x, well, you can just do the 4th root of 81. The names for these are the root or the square root for when it's 2, the cube root when it's 3, the 4th root and the 5th root when it's 5, and you can just say the xth root if you really want to for any number x, for any power rather x, and the power I'm talking about a to the x, so this x here. We can also estimate roots. For example, if I asked you for the square root of 249, you wouldn't know that. But what we do know is that, for example, 15 squared is 225 and 16 squared is 256. And we know that 249 is somewhere between them, so we can write it on a number line. If this is 225, this is 230, this is 240, 250, 260. And if we know 256, which is about here, is 16 squared, and if we know that 15 squared, which is here, and we want the root of 249, which is around here. So we can estimate that if we are going between 15 and 16 here, and we want this part around here, well, that's halfway, around halfway. This is about 3/4 of the way. This is just above 3/4 of the way. So we can estimate that actually the root of 249 is around 15.8. And if we do that on a calculator, 15.8 squared gives 249.64. Now, the root of 249, according to the calculator, is 15.7797. And you can see if we round that, we will actually get 15.8. We did an incredible estimation there, and we got practically the right answer, because we got it right to 1 decimal place, which is pretty good. Sometimes you get fractional indices. For example, if we get 81 to the power of 3/2. Well, first we look at the rules of indices. X to the power of a/b is equal to the bth root of x to the a. And this can also be rewritten as the bth root of x all to the power of a, which is the excellent thing with manipulating indices. Now, going back to this, 81 to the power of 3/2, well, now we know we can rewrite that as 81 cubed and the square root of that. Or we can write the square root of 81 all cubed. And this makes it easier because we know the square root of 81 is 9 or minus 9. So we know that this is equal to plus or minus 9. And we know then that 81 to the 3/2 is plus or minus 9 to the power of 3. And we know that is equal to 9 times 9 times 9, which is equal to 729. Now, if it's a positive 9, it will be 729. However, if we use negative 9, we would get minus 729. So we should write plus or minus 729. Another example is 27 to the power of 5/3. 27 to the power of 5/3 is the cube root of 27 to the power of 5. The cube root of 27 to the power of 5, well, we can look at the cube root of 27 first, and then do the 5th power of that. The cube root of 27 is 3, and it's not minus 3 because it can only be 3. So 3 to the 5. And we can calculate that by doing 3 times 3 times 3 times 3, which will give you 5 times, in fact, which will give you 243. And that is the equivalent of 27 to the power of 5/3. Now we can also do negative roots. So if we had 4 to the power of 2/4, minus 2/4 in fact, then we should look at this law. If we have x to the minus 1, that is equal to 1 over x to the 1, or 1 over x. If we have x to the minus a, then that is equal to 1 over x to the a. And therefore we can apply this here. We can say that is equal to 1 over 4 to the power of 2/4. And we can actually simplify the 2/4. We can say 1 over 4 to the half. Now 4 to the half is, so we can say 1 over, it's just going to be the square root of 4. And we know that can either be 2 or minus 2. So our final answer is plus or minus a half. Say we have an area. The area of a circle is 32 centimeters squared. Sometimes we want to leave our answers in their exact form, and that involves using surds and expressing our answers in terms of pi. So if we have pi r squared equals 32, r squared equals 32 over pi, and r equals the root of 32 over pi. Now we know the radius can only be positive, so we're only taking the positive version of this answer. And then if we have, we know from the rules of surds and powers, in fact, that root a over root b is the same as root a over b, and we know that a to the power of x over b to the power of x is the same as a over b all to the power of x. That means our radius can be expressed as the root of 32 over the root of pi. And if we want to look at the root of 32, well, we can split that down into the root of 16 times the root of 2, because, again, another rule, the root of a, b is the same as the root of a times the root of b. And the important thing here is that 16 is a square number. So now we can rewrite that as 4 root 2 over root pi. We can either leave our answer like this, or in centimeters in fact, or what we can do is rationalize it, which will be done on the next slide. Well, if we have 4 root 2 over root pi, and we want to rationalize this, rationalizing means we're getting rid of the surd on the bottom. So to get rid of root pi and get a nicer number on the bottom, we can just multiply by root pi. So 4 root 2 over root pi times root pi over root pi. And we know root pi over root pi is 1 over 1. Multiplying a fraction by 1 does not do anything to the fraction, the value of the fraction, so it should be fine. So if we multiply by root pi on the top, and we multiply on the bottom root pi times root pi is pi, and this is our rationalized form. Now, generally speaking, you wouldn't really want pi on the bottom. You'd want a nice integer, but sometimes that is the case. If we looked at a different expression, if we looked at the root of 72 over the root of 8, well, we know that the root of 72 over the root of 8 is the same as root 72 over 8. That's the same as root 9, and that is the same as plus or minus 3. If we were to rationalize something else, so say x root 2 over root 3, we can multiply by root 3 on the top and bottom, as we've seen, and that gives x root 2 root 3 over root 3 times root 3, which is 3. And we can change the root 2 root 3 to root 6, so x root 6 over 3. And that is your rationalized form. Sometimes we will not have a single term on the bottom. For example, as the denominator, we could have 2 plus root 3, and on the top 7 plus root 5. And if we wanted to rationalize this, we could go by the old rule and multiply by 2 plus root 3 on the top and bottom. And the top will be 7 plus root 5, 2 plus root 3. We can expand that in a minute. But the bottom, now if we expand that, we do 2 times 2, which is 4. Then we do 2 times root 3 and another 2 times root 3, so that is 4 root 3, and the last two terms root 3, which is 3, and then we see that we get 7 plus root 5 over 2 plus root 3 over 4 plus, in fact we can say 7 plus 4 over 4 root 3. What you may have realized is we still have a surd on the bottom, and that is exactly what we don't want. What we could do instead is multiply by 2 minus root 3. This will make sure the middle term cancels out, because if we have 2 plus root 3, 2 minus root 3, that gives 4 plus 2 root 3 minus 2 root 3 minus 3. And these are equal to 0, so we just get 4 minus 3, which is 1. If we do that properly, so if we said 7 plus root 5 over 2 plus root 3 times 2 minus root 3 over 2 minus root 3, on the top, well, we'd get 14 plus 2 root 5 minus 7 root 3 minus root 15, and on the bottom we would get 1, as we have demonstrated here. We could try simplifying the top, but you wouldn't really get anywhere, because we've got surds with different numbers inside. We've got root of 5, root of 3 and root of 15, and it would just be a headache to try and make them all one roots. But now we can just rewrite it as 14 plus 2 root 5 minus 7 root 3 minus root 15. And that is your final rationalized form of the expression here. Finally, in this video we'll be looking at standard form. Standard form is a way to express really big numbers and really small numbers as something times 10 to the power of something. So if we had, it's a bit like place value, but slightly different. So if we had 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, well, we know that is 4 billion, because we've got 9 zeros in there. And we can actually express this as 4 times 1 billion. Now this part can be expressed as 10 to the power of 9, because this is the same as 10 times 10 times 10, 9 times. Now 4 times 10 to the 9, 4 times 10 to the 9, that is your answer in standard form. We have rewritten it in a way easier, a way shorter, a way more efficient method. Generally speaking, with standard form we have a times 10 to the power of n. A is a number that's between 1 and 10. It does not take the value of 10. It does take the value of 1. So a can be 1, it cannot be 10. And that's really important to know. And standard form can be useful for small numbers as well. If we have 0.000625, well, we know that this is 6.25 times 10 to the minus something, because this time if you look back at this, at the first bit of this video, we looked at negative indices. And negative indices, if we have 10 to the minus x, that means 1 over 10 to the x, which means you're dividing by 10 to the power of something. And 6.25 divided by 10 to the power of something will give you this. And to find that something, we need to move, in quotation marks, the decimal place. Moves 1, moves 2, moves 3, and it moves 4. We're moving 4 places to the right, and we're doing the opposite of that here, so we're moving 4 spaces to the left to get from 6.25 to 0.000625. That is your answer in standard form. Sometimes you may get asked to convert between standard form and the normal way of writing numbers. So if we have 2.76 times 10 to the power of 3 divided by 10 to the power of 5, well, first let's make a note of the following rule. X to the power of a times x to the power of b is the same as x to the power of a plus b, and x to the power of a divided by x to the power of b is the same as x to the power of a minus b. We can rewrite this here as 2.76 times 10 to the power of 3 divided by 10 to the power of 5. And then using the rule on the right, 2.76 times 10 to the power of 3 minus 5. So 2.76 times 10 to the power of minus 2. 10 to the power of minus 2 means we're moving the decimal place 2 places to the left. So that becomes 0.0276. And that is your final answer, written not in standard form. Thank you very much for watching. Please subscribe for more maths videos.